We're going to do the first lesson in polar calculus. Here's our warm-up. You like my icon with my freezing polar guy. Just a review of some polar coordinates and going from rectangular to polar. Recall that r cosine theta is x. So this is x is equal to 2. Here's r cosine theta again, which is x, minus r sine theta, which is y, which is equal to 2. So this is the graph of a vertical line, just written in polar form. The graph of a diagonal line, written in polar form. And then if you recall from triangles, r squared is x squared plus y squared is equal to 4 r cosine theta, which is x. Translate the following Cartesian coordinates, that's x comma y, into polar coordinates. Well, remember that polar coordinates I need r comma theta. So for the radius, if I have, remember, if r squared is x squared plus y squared, then r would be the square root of negative root 3 squared plus negative 1 squared, which of course is the square root of 3 plus 1, which is square root of 4, which is 2. So r is 2. And then again, theta, if you remember from triangles, would be y over x, so that would be negative 1 over negative root 3. And if you remember from your unit circle, when x is negative and y is negative, you're in quadrant 3. So who has a tangent of 1 over root 3 but is in quadrant 3? And that would be 7 pi over 6. You'll be doing a polar review tomorrow if all of this stuff looks kind of crazy to you. You'll be going to the computer lab tomorrow and looking up some websites where you can review all of this pre-calculus polar stuff. But on to some calculus with polars. Look at that pretty curve. Isn't that nice? You're not going to do nothing with it. I just thought I'd show you to you. It reminds me of a spirograph. I don't know if any of you are old enough to remember what spirographs are. Here is a parametric curve. Remember I showed you this? I told you it reminded me of an ice skater. And we learned how to do calculus with finding the slope of a parametrized curve, dy dx. Remember, dy dx is not the rate of change of y with respect to x, even though this curve is expressed as a composition of a horizontal component and a vertical component. I still wanted to get dy dx, and when I did that, I made a ratio saying, well, what is the rate of change of y? Well, it's the rate of change of y with respect to t. The rate of change of x is the rate of change of x with respect to t. And then we had our dt's cancel out. Well, maybe you won't be surprised that to find the slope of a polar curve is very similar. To find the slope of a polar curve, make sure you can see the bottom of the screen here. The slope of a polar curve is still a ratio, but it's instead of dy dt, it's dy d theta over dx d theta. So if you look at this though, the derivative of y with respect to theta, in polars, y is the same as r sine theta, and the derivative of x with respect to theta is the derivative of x with respect to theta. Now the problem is I'm taking the derivative of a product, right? If you take the derivative, I'm going to put this down here maybe. The derivative of a product takes the product rule, right? Remember the product rule? Product rule never changes. The derivative of product is the first function, r, times the derivative of sine, which is cosine, plus the second function, sine, times the derivative of the first, the derivative of r with respect to theta, I'm just going to call r prime. So I should do that for, that's the numerator, and the denominator. And all I did was take this expression. If you notice, most books take this is my numerator, and use the commutative property and wrote the r prime first. The denominator, again, is using the product rule here. The first function, r, it's over here, times the derivative of cosine, which is negative sine, plus the second function cosine, times the derivative of r. And most books like to line it up this way with the r primes first. That's your formula that you've got to memorize. Now I don't always, if I don't use this formula so often, so if I forget it, it's really no big deal, right? As long as I do remember the definition of how I find dy dx when I've got theta hanging around. So for example, to find the expression for the slope of the curve defined as r equals 2 minus 3 sine theta, I can remember that formula and just plug and chug, which is fine. You see that? Maybe the top is cut off, huh? But if you forget the formula, if you just remember that y, you do have to remember y is defined as r sine theta. So here's r. 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 Sine theta. What is x defined as? X is r times cosine theta. There's r times cosine theta. So if I take the derivative of y with respect to theta, again it is the first function, 2 minus 3 sine theta, times the derivative of sine, which is cosine, plus sine times the derivative of r, which would be negative 3 sine theta. So let me write that out. dy d theta would be the first function, times the derivative of sine, which is cosine, plus sine theta, the second function, times the derivative of r. Now calculate dx d theta, the first function, times the derivative of cosine, which is not sine, but negative sine, plus the second function cosine, times the derivative of r, which is negative 3 sine theta. Then make a ratio of the two. So I have, using again the commutative property of addition, negative 3 sine theta times sine theta plus 2 minus 3 sine theta, cosine theta, all over negative 3 sine theta, cosine theta, minus 2 minus 3 sine theta. And no, don't bother to distribute, combine, and certainly for God's sakes don't cancel anything. Right? You don't have matching factors all around. Done and done. Notice that if you had used the formula from the screen previously, right, my formula for dy dx is r prime sine theta plus r cosine theta over r prime cosine theta minus r sine theta, which is exactly what we have here. So if I remembered my formula straight up, I would have just looked at r, take its derivative, multiplied it times sine, copied r, multiplied it by cosine, and done the same thing in the reverse order, taking the derivative times cosine minus the original r times sine in the denominator. But if I forgot that or forgot the order, I can just refer back here, and I will get to the same place. Now that I found dy dx, what if they ask me to find the slope of the curve at particular points? This is going to be with your calculator. So if you get your calculator out and put it into polar mode, darn it, sorry. There's my curve, and if you hit trace, you can enter thetas. So if you enter the theta pi, you can see that at theta pi, your x position is -2 and your y position is 0. So if I want you to find me the slope of the curve at that indicated point, I have to know that this is r, 2 is r, and theta is pi, and that's why I plugged pi in. And here's the point, x comma y, x to y 0, that's rectangular coordinates, but this is the polar coordinate, same place, 2, radius of 2, and theta of pi. That's where I landed, and I want to find the slope of the curve. So I can use the formula on the previous slide and plug in pi to that formula. So I can do dy dx at theta equals pi over 2, or I can use my calculator then if you go to second trace, choice 2 is dy dx. And there I am already at theta equals pi. And I said, what is dy dx? And there I have it. There's a screenshot. I can actually ask the calculator also to draw the tangent there. So now if I give you other points, just plug and chug. What about at 2, 0? Well, at 2, 0, theta is what? I'm right on the other side at 2, 0. Right, radius 2, theta 0. And as you can see, if I draw a slope there, it should be a negative slope, right? Negative slope, and if you can see with the symmetry, that you shouldn't be surprised that you got negative 0.666. Negative 1 pi over 2. Do the same thing. Second trace, I want dy dx at theta is equal to pi divided by 2. Hey, look at that. Does that surprise you? That dy dx is 0 at r equals negative 1 and theta equals pi over 2. So right here. There's that tangent line. Out negative 5, 3 pi over 2. Bet you can guess where that is. That's going to be down here. And can you guess what that slope is going to be? There you go. So, in your homework problems, number 42, I want you to repeat this process. Find the derivative expression, then use your calculator to find the derivative at a point, because on the AP problem, AP test, that's how this is going to go. Right, you're going to have a calculator for these, and when you're allowed to use your calculator to find the derivative at a point. But if they ask you for the derivative expression, so let me go back to those directions, right? Find the expression for the slope of the curve. That says to me, use my formula for dy dx. Okay. But if I just want the slope at a point, that's where I'm going to use my calculator. Okay, so finding slopes of tangents on a polar curve, finding the expression, and finding the value at a point. Next, find the length of a polar curve. to find the length of a polar curve, I bet you're going to be shocked at that formula. Right? It is an integral. It's an integral of the square root of r squared. Remember when we were in rectangular form, that was just 1 plus dy dx squared. When we were in parametric polars, it was dx dt squared plus dy dt squared. And here we are in polars, and it is the radius squared plus dr d theta squared. So if I gave you this example, where I asked you to find the length of the cardioid, where the radius was equal to 1 minus cosine theta, the only thing you need, r is right there, and you just need to take r and square it, and in here you need r prime. The derivative of 1 minus cosine theta is sine theta. So you're going to put sine theta there. Again, you're going to have your calculator, although this turns out to be very nice with some trig identities. Right? So the length of the cardioid, it takes from 0 to 2 pi, one cycle. 0 to 2 pi to complete one cycle, so the length of this curve is 0 to 2 pi. There's r. There's dr d theta. And I just put this into my calculator, f and inted, and I got 8. Can you see that some of these curves with the beautiful symmetry with trig, there's such, nice symmetry with a lot of these things, whether you're in polar or rectangular form. I could have just done the length of the curve from 0 to pi and multiplied by what? Right? Right, so there's a lot of times when you can do this. What we're going to be doing next is the area. That becomes real tricky. The area, using integration to find the area with polar curves or the intersection of polar curves, is kind of tricky. So that's going to be for another lesson. Remember, tomorrow, please go to the computer lab. (253), and you're going to go to math groups, log on, and find the PowerPoint polar review, and it will be no calculus. It will just be some pre-cal review of some of the formulas I showed you in the warm-up, the straightforward rectangular to polar, as well as, remember what the form of a cardioid versus the form of a limosome versus the form of a rose, and 4 petals and 2 petals and blah, 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 blah. Will be in a bunch of websites where you can go and practice and drill some of that stuff. And of course you can always just look it up in a pre-cal book. I'm going to go all the way back to the beginning in case you didn't get the homework assignment on the warm-up. Oh, that's because it wasn't there on the warm-up. The homework assignment is adjusted from your